Okay, so numbers 85 and 89 are gas stoichiometry problems. Now in chapters 10 and 11, we did more traditional stoichiometry problems where we go back and forth between grams and moles of a substance. So if you look here in red, I've drawn a diagram, and the left side of this diagram may look familiar to you because that's the framework we've used in chapters 10 and 11. Right? We use molar mass to go back and forth between grams and moles of a substance. We use the mole ratio to go back and forth between moles of one substance and moles of another substance. Information from Chapter 13 allows us to build on this existing framework. So now if we have a gas, we have the ideal gas law. The ideal gas law allows us to go back and forth between moles of a substance and liters of a substance. Also, if we have two gases that are at the same, and we're operating under constant pressure, we can use the volume ratio to go from liters of one substance to liters of another substance. Right? You get the numbers from the volume for the volume ratio from the balanced chemical equation, just like you did from the mole ratio. And again, one caveat is you only use the volume ratio for gases. Problem number 85 gives us a chemical reaction, and it says we start with 6.5 liters of hydrogen sulfide, and it reacts at a pressure of 2 atmospheres and a temperature of 290 Kelvin. We want to know how much water vapor is produced in this reaction. So this means we need to go from liters of one substance to grams of another. Basically from liters of A to grams of A. Grams of B. So there's several paths we can take to get there. One I chose is to start off by using the volume ratio to go from liters of hydrogen sulfide to liters of water. Because both of them are gases, we can do this. From there we can use the ideal gas law to go from liters of water vapor to moles of water vapor, and then the molar mass to go from moles to grams. So again, the first thing I did here was use the volume ratio. And we get the numbers from the volume ratio from the balanced chemical equation. They're these coefficients. What it tells us is that each 2 liters of hydrogen sulfide that will react will produce 2 liters of water. Basically the same thing as saying it's a 1-to-1 ratio. So our 6.5 liters of hydrogen sulfide will end up producing 6.5 liters of water vapor. From here, now we have a volume. We were given a pressure and a temperature. We can put all this information into the ideal gas law to solve for the number of moles. Right? The ideal gas law allows us to convert between volume and moles. Doing so yields 0.55 moles of water. From here, we're at moles of water. We need grams, so we just use the molar mass of water to get grams. Multiplying by the molar mass allows us to cancel out moles of water, and it'll give us 9.9 grams of H2O for our final answer. In number 89, we're going in the opposite direction. So we're given a mass of potassium chlorate. Potassium chlorate is KClO3. It's a solid, and we're asked how many liters of oxygen will be produced if we decompose 20.8 grams of potassium chlorate. Just like before, we are given pressures and temperatures to work with as well. So in this case, we're starting out with grams of one substance. Whereas in the last problem, there were several pathways we could take to get to our final answer. In this, there's only really one. And the reason that there's only really one is because potassium chlorate is a solid. So we can't use the ideal gas law to go from moles of potassium chlorate to liters of potassium chlorate, and we can't use a volume ratio to go between potassium chlorate and oxygen. So what we're going to do here is we're going to start with grams. We use the molar mass of potassium chlorate to get from grams of KClO3 to moles of KClO3. That's our first step here. So we cancel out our grams of KClO3. Once we have our moles of KClO3, we can use the mole ratio. We get, again, these numbers from the balanced chemical equation. This mole ratio will allow us to go back and forth between potassium chlorate and oxygen. We want to make sure oxygen is at the top so that we can cancel out our potassium chlorate. If we arrange our conversion factors properly, this will leave us with 0.255 moles of O2 being produced. Now that we've got our moles of oxygen, it's just a matter of plugging these moles into our ideal gas law, along with the temperature and pressure conditions given to us in the problem. Right? We're told that there's a pressure of 1 atmosphere and a temperature of 273 Kelvin, because it's at STP, and the thing to remember is that STP equals 273 Kelvin in 1 atmosphere. Once we plug it in, we can solve for V, and we get a volume of 5.72 liters being produced.